Bismillah, alhamdulillah, wassalatu wassalamu ala rasulillah. This is the last part about section 4.3, and we will solve some exercises about curve sketching. Here he is asking these parts about each question: intervals of increase, decrease, local maximum, minimum, intervals of concavity. Use the information to sketch the graph. You may want to check your work with graphing calculator or computer. Uh, Well, I'd like always to determine the domain of the function. This is a polynomial, so the domain or real numbers. I'd like also to check the horizontal asymptotes of the function. Actually, there is no horizontal asymptotes because the limit of f of x when x goes to infinity is the limit when x cubed goes to infinity. We take the highest power, the term with the highest power, and infinity cube is infinity. So when x goes to infinity, the function goes to infinity. This means that the graph is like this from the right. I can also find the limit when x approaches negative infinity of f of x to see what happens to the graph from the left. And again, I will use the highest power, the term with the highest power. And when you raise negative infinity to the power 3, you get negative infinity. So it will go to negative infinity from the left. So at least I know the behavior, the end, we call it the end behavior of the graph. The domain is all real numbers, so no vertical asymptote. So here we don't have no vertical asymptote and no horizontal asymptote because the limit is infinity and negative infinity. Good. So let us start answering the questions. Intervals of increase and decrease, local maximum and minimum. I need to find the first derivative. I can also find the y-intercept. If I put x0, y is 4, so I know the y-intercept of the graph. I can find the x-intercepts if I like, but I'll have to solve this equation. You can use the calculator to find the x-intercepts if you like. Well, the first derivative is 3x squared minus 6x. And if I take 3x as a common factor, I have x minus 2. So 0 and 2 are the zeros of f prime. Coefficient of x squared is positive between the zeros. The sign of f prime would be negative. So f is increasing, decreasing, increasing here. If he is asking about intervals of increase or decrease, so I will write it for him. Increase on negative infinity to 0, union 2 to infinity, and decrease on 0 to 2. In part B, he is asking about local maximum and local minimum. I have a local maximum at x equals to 0. So f of 0 is the local maximum, and f of 0 is 4. So the y-intercept in this case is the local maximum. This y-intercept is the local maximum. And I have a local minimum at 2, so f of 2 is the local minimum. And if I replace x by 2 in the definition of f of x, so 2 to the power 3, that's 8, minus 3 times 2 to the power 2 plus 4, the answer is 0. So this is an x-intercept. I have an x-intercept 2 and 0. So I have 2 and 0 here. There is a local minimum. Okay. So I can say that the graph goes after this to infinity if you like. And I can guess the graph. I think this would be the graph of the function. But I'll find more uh, information. Intervals of concavity and inflection points. This needs f double prime. F double prime would be 6x minus 6. If I put it equals to 0, then x is 1. So I can do a table for f double prime. If x is greater than 1, f double prime would be positive, negative, concave down, concave up. So I can answer part C now, intervals of concavity and inflection points. Well, it's concave up. F is concave up on 1 to infinity. It's concave down on negative infinity to 1. And I have an inflection point at 1. X is 1. So x is 1, put it here. F of 1 is 1 minus 3, negative 2 plus 4 is 2. So 1 and 2 is an inflection point. This is 1 and 2. This is an inflection point. So that's it. Partly use the information to sketch the graph. Let me check this graph now. Is it okay? From negative infinity to 0, it is increasing. Yes. From 0 to 2, it's decreasing. That's correct. From 2 to infinity, it's increasing. So everything is fine. Concavity from negative infinity to 1 up to here, it is concave down. And now it's concave up. And the point 1 and 2 is inflection point. So actually, this is the graph. Let me maybe make it nicer. So 1, 2, 3, 4. 1, 2. This is the point 1 and 2. This is the inflection point. So it's here. The graph is concave up. And here it starts to be concave down. So this is the graph of the function. You can choose more points. If you choose more points, you will find exactly what is the other x-intercept here. And that's it. Maybe also you'll find out whether the graph goes like this or maybe like this. But by choosing more points, you can make it more accurate. But this is the graph of the function f of x, and it satisfies everything. All the information here are satisfied in this graph. Another function, the domain or real numbers. Limit f of x when x goes to infinity. X to the power infinity is infinity. The highest power is half x to the power 4. And limit f of x when x goes to negative infinity. Half x to the power 4 also. Negative infinity to the power 4 is positive infinity. So now for this curve, from the right it goes up and from the left it goes up. It's not like the previous one. All right. Of course, also this is a polynomial, so no horizontal asymptote, no vertical asymptote. Okay, no horizontal asymptote because the limit goes to infinity. All right, what is the y-intercept? The y-intercept is, if you put x0, y is 3. The x-intercept, you can find the x-intercept by solving the quadratic equation half x squared minus 4x plus 3, and then writing x squared equals each of these roots. but it's not that important for me, the x-intercepts. I'll go immediately and find f prime. 4 times half is 2x to the power 3 minus 8x. So I can take 2x as a common factor. So I have x squared minus 4. And this is 2x times x minus 2 times x plus 2. So I have negative 2, 0, and 2. These are the zeros of f prime. And you can see that all of them are zeros of multiplicity 1. So if I just take 3, substitute with 3, all of them would be positive. So this is negative, positive, negative, decreasing, increasing, decreasing, increasing. So part A would be increasing on negative 2 to 0, union 2 to infinity, and the function f is decreasing on negative infinity to negative 2, union 0 to 2. And part B, I have a local maximum at what? At 0. So f of 0 is a local maximum at f of 0 of 3. So again, 0, 3, the y-intercept here is a local maximum. That's okay. And I have two local minimums or minima at negative 2, f of negative 2. And f of negative 2 is half times negative 2 to the power 4 minus 4 times negative 2 to the power 2 plus 3. And the answer is 67. And you can, it's not 67, there is a problem here. A very large number. Oh, negative 5. The answer is negative 5. Using the calculator, it's negative 5. You can notice if you replace negative x, if you find f of negative x, it would be equal to f of x. So f of negative x equals f of x. This means that the function is even. So the graph is symmetric about the y-axis. And we are starting to see this, that the graph is symmetric about the y-axis. So f of 2 is also a minimum, and it's also equal to 5, equals to 5, because f of 2 equals to f of negative 2. So at 2, this point is, these 2 points are local minimums. So I can expect the graph now. I can say that it goes up like this. And from here also it goes up like this. Okay. And you have to go similarly because the graph is symmetric about the y-axis. Okay, this is a tentative graph. Afterwards, I will sketch the graph. And it seems it goes like this. It seems that this is the graph of the function. Okay. So let us check more information. So to find the intervals of concavity, concave up, concave down, inflection points, I need f double prime. F double prime 2 times 3 is 6x squared minus 8. So x squared would be 8 over 6 or 4 over 3. So x would be plus or minus 2 over square root of 3. And 2 over square root of 3 is approximately 1.2. So plus or minus 1.2 would be the zeros of f double prime. And if double prime has degree 2, the coefficient of x squared is positive between the zeros, it's negative, and here positive. Concave up, concave down, concave up. So concave part C, concave down from negative 2 over square root of 3 to 2 over square root of 3, and concave up from negative infinity to negative 2 over square root of 3 union 2 over square root of 3 to infinity. And inflection points, I have two inflection points, negative 2 over square root of 3 and f of negative 2 over square root of 3, and also 2 over square root of 3 and f of 2 over square root of 3, and both will give the same answer because the function is symmetric about the y-axis. So 0.5 times 2 over square root of 3 to the power 4 minus 4 times 2 over square root of 3 to the power 2 and plus 3. The answer is negative 13 over 9. And negative 13 over 9 is negative 1.4. So this is 1.2 and this is negative 1.4. So 1.2 and negative 1.4, it's somewhere here, somewhere here. These are the inflection points. So the curve, the graph satisfies all the conditions. Concave up to this one, concave down up to here, concave up again, decreasing up to negative 2, then increasing, then decreasing from 0 to 2, then increasing, everything is fine. So actually this is the graph of this function, and I can now graph it more accurately. So 1, 2, 3, this is a local maximum, 2 and negative 5, and negative 2 and negative 5 are local minimums. So this is a local minimum, this is a local minimum. 1.2 and negative 1.4 somewhere here is the inflection point, and negative 1.2 also somewhere here is the inflection point. So here the graph is concave up, and here it's concave down up to here, concave down. Okay, then it starts to be concave up, and then it goes up to infinity, and here concave up and it goes to infinity. And you can take more points to sketch more accurate graph. Please excuse my graph by hand. So this is the graph of the function f of x. Satisfies all the conditions. Another function, the domain of gt, or real numbers. Again, it's a polynomial. Limit g of t when t goes to infinity is equal to limit g of t when t goes to negative infinity is equal to infinity, because the highest power is t to the power 4 and the coefficient is positive. So again, this graph goes up from the right and from the left, but this function is not even, neither even nor odd. Because g of negative t is not equal to g of t, and also g of negative t is not equal to negative g of t. All right, let us find no vertical asymptote, no horizontal asymptote as usual. It's a polynomial. So let us find g prime of t. 12t cube minus 3 times 8, 24t square. Well, I can take 12t square as a common factor. So I have t minus 2. Okay, this is square. So I have 0 and 2, the zeros of f prime. And notice that 0 is a 0 of multiplicity 2, while g prime, sorry. So if I choose a number greater than 2, 3, this would be positive. 2 is a 0 of multiplicity 1, so this would be negative. 0 is a 0 of multiplicity 2, this would be negative. So increasing, increasing, and decreasing. You can find more about the signs in the first two parts of this section. So part A, the function is decreasing on negative infinity to 0, union 0 to 2. I can say from negative infinity to 2 because the function is defined at 0, there is no problem. And increasing on 2 to infinity. I have a local minimum at x equals to 2, so f of g of 2 is a local minimum. And I can find g of 2 by replacing t by 2, so 3 times 2 to the power 4 minus 8 times 2 to the power 3 plus 12. And the answer is negative 4. So negative 4 is a local minimum, and there is no local maximum. All right, let us find g double prime of t. So 2 and negative 4 is a local minimum. And at 0, no local minimum, no local maximum. But g prime is 0, so I think I have a horizontal, of course, I have a horizontal tangent. And since it goes to infinity from here and goes to infinity from here, so I guess that this is the graph. It's decreasing from negative infinity to 2, increasing from 2 to infinity. So everything is fine. If you put t0, 0, 12, so 0, 12 is the y-intercept. So it doesn't pass by 0, 0. So at 0, 12 here. So this will go up to here, and I'll have a tangent 0 here, and then it will continue like this. Okay? Because nothing here at 0, 0. So again, it's okay from negative infinity to 0 to 2, actually. It is down and decreasing, and from 2 to infinity is increasing. So everything up to here now is okay. Now let us find concavity. G double prime t would be 3 times 12. That's 36 t square minus 2 times 4, that's 48t. I can take 12 as a common factor, 12t actually. So I have 3t minus 4. Okay, yeah. Yes. So I have two zeros of g double prime. Either t is 0 or t is 4 over 3. And f double prime is degree 2, or sorry, g double prime is degree 2. So between the zeros, the sign is opposite to the sign of t squared. So it would be negative here, positive here, positive here. Concave up, concave down, concave up. So it's concave down from 0 to 4 over 3. And concave up from negative infinity to 0, union from 4 over 3 to infinity. And I have two inflection points at 0, 12, and at 4 over 3, and f of 4 over 3. I replace x by 4 over 3 in the definition of g of t, and the answer is 68 over 27. And this number is 2.5 approximately. And 4 over 3 is 1.3. So 0, 12, this point is an inflection point. So here, concave up before 0, and after 0, concave down. That's excellent. And then the point 1.3, so if this is 1, okay, is this 1? No, the local minimum at 2, so this is 2. So here, somewhere here, 1 point something and 2.5 is an inflection point. So it was concave down, and then it becomes concave up here, okay? Concave up from 4 over 3 up to infinity. So that's the graph actually, but I need to, let me write it again more accurately. So this is 1, this is 2, the point 1.3. Well, here I go 6, 8, 10, 12. I go 2 by 2, maybe 4 by 4. Okay, 4, 8, 12. So 1.3 and 2.5 is somewhere here. This is an inflection point. 0, 12 somewhere here. This is also an inflection point. And 2 and negative 4 is the minimum. So this is the minimum. So it's concave up to here, and then it goes like this. Okay. And here it becomes concave down. Okay. And then here it has a tangent line. So it's concave down up to here, tangent line. And this is an inflection point, and it becomes concave up. Continues to infinity. Of course, you can take this more up. Okay. So this is the graph of this function. It satisfies all the conditions. You can choose more points to check that everything is fine. Another function. Well, what is the domain here of capital F? Why we have a square root. 6 minus x should be greater than or equal to 0. So 6 is greater than or equal to 6, or x is less than or equal to 6. So the domain is from negative infinity to 6. That's the domain, so the graph would be from negative infinity to 6, nothing after 6. Okay. Now, can I find here the limit when x approaches infinity? No, because x does not go to infinity. But I can find the limit when x approaches negative infinity. Well, if x is negative infinity, then negative infinity would be infinity plus 6 infinity, square root of infinity, infinity times negative infinity. So infinity times negative infinity is negative infinity. So that's important. I know now that the graph starts at 6 and at the end it goes to negative infinity from the left. That's excellent. And because of that, it has no horizontal asymptotes. I did not get a number. And at 6, I do not have anything. If I take the limit when x approaches 6, let me see what happens. Well, 6 is a number in the domain. So if I replace x by 6, I get 6 minus 6, 0. So I get 0. So actually the point 6, 0 is just an x-intercept. So this point is an x-intercept. And this is the last point of the graph. All right, what else? So no vertical asymptote, no horizontal asymptote. Let us go to f capital prime. I'll use the product rule. Derivative of x is 1 times the square root plus x times. The derivative of the square root is 1 over 2 times the square root times the derivative of what is inside the square root, the radicand, negative 1. So let me add these two fractions. So I'll have 2 times the square root of 6 minus x, and here 2 times square root of 6 minus x times square root of 6 minus x. I will have 6 minus x plus negative x or minus x. So 2 times 6 is 12, minus 2x minus x is minus 3x over 2 times 6 minus square root of 6 minus x. So this is f capital, f capital prime. Notice that 6 here, f prime does not exist at 6. So f prime does not exist at x equals 6. And 6 is in the domain. 6 is in the domain of capital F. So there is something at 6. I won't be able to find the tangent line because the tangent line is not defined. The derivative is not defined at 6. Okay. And there is a 0, but 2 times the square root is always positive. So the sign of f prime depends on the numerator. So let us find the 0 of the numerator. 3x is 12 or x is 4. So the 0 of the numerator is 4. Around 4, f capital prime will change its sign. If I choose 5, f capital prime would be negative, positive. So it's increasing here and decreasing here. So the function is increasing from negative infinity to 4 and decreasing from 4 to infinity. So 4 is an important number. If this is 4, and I have a local maximum at 4. So f of 4 is a local maximum. And f of 4 would be 4 times 6 minus 4 under the square root. 4 times square root of 2. And 4 times square root of 2 is approximately 5.7. So here, somewhere here, 5.7 this is a maximum. So it seems that the function goes like this, okay? And that's why at 6, the derivative, I cannot draw a tangent line, so the derivative is not defined. And then notice that up to 6, not from 4 to infinity. Yeah, this is not correct. We only work from negative infinity to 6, because 6 is the last number. We don't go to infinity here. So we have just 6. Let me even cancel this and make it up to 6 only. So it's increasing from negative infinity to 4, increasing and decreasing. It's okay, decreasing from 4 to 6. That's excellent. And I have a local maximum. So up to now, everything's fine. Let me find. Well, what happens? What are the x-intercepts? 6 is an x-intercept and 0 also. 0 is an x-intercept. So this point is an x-intercept. And if the graph is always increasing, so it's maybe going like this, because now it's increasing, and when x goes to negative infinity, the graph goes to negative infinity. So maybe this is the graph of the function. Let us find f double prime, capital double prime, and see what happens. Well, I will use this definition of f prime, and I will use the quotient rule. So square the denominator, raise it to the power 2. The derivative of the numerator is negative 3 times 2 square root of 6 minus x minus 12 minus 3x, the numerator, times the derivative of the denominator, 2 square root of. So the derivative of 2 square root of is 2 over 1 over 2 square root of 6 minus x, and 2 will be cancelled with the 2, times negative 1, because the derivative of 6 minus x. So this is the derivative of 2 times the square root of 6 minus x. Now, I'd like to multiply here up and down by square root of 6 minus x to get rid of the square root of 6 minus x. So I will have negative 3 times 2, that's negative 6. Square root of 6 minus x times square root of 6 minus x, that's 6 minus x, minus 12 minus 3x. Now, I have minus 1 here, so I can write it plus. And square root of 6 minus x will be cancelled with square root of 6 minus x. So that's it. Okay, I'll have plus 12 minus 3x. Excellent. Over 4 and 6 minus x to the power 1 times 6 minus x to the power half. I will have 6 minus x to the power 3 over 2. So this is negative 36 plus 6x plus 12 minus 3x. So negative 36 plus 12 is negative 24. Yes. And 6x minus 3x is plus 3x. 6 minus 3 is 3. So this is f double prime. Again, f double prime does not exist at 6. And notice that 3 over 2 here yeah, we at 6 it's not defined, but this is square root. Okay, so we cannot choose x greater than 6. X is the domain is from negative infinity to 6. So what is here? What is the zero of f double prime? 3x equals 24, okay. Negative 24 plus 3x is 0, so 3x is 24 and x is 8. But 8 does not belong to the domain of f. In fact, x is always less than 6. Okay, we cannot go beyond 6 because it's not in the domain. So in all of this interval, because at 8, if double prime changes its sign, and also at 6, but 6 and 8 are, 6 is here, but 8 is after that. So what happens before 6? If you replace 0, for example, if you put x 0, then f double prime, f capital would be always negative. So from negative infinity to 6, if double prime is always negative. So the answer to part C would be the function is concave down from negative infinity to 6, and it's not concave up at all, and no inflection points, no IP. So the function is always concave down, and this agrees with this graph. So everything agrees with this graph now, and no inflection points, so that's actually the graph. If you want 1, 2, 3, 4, 5, 6, so this is 6, 4 and what, and 5.7. So 1, 2, 3, 4, 5, 6, so this is 5.7. This is the maximum, and 0, 0. So the graph is like this. Of course, here it is not straight line. It's always concave down, okay? It's always concave down. You know, concavity is the art. When you draw the graph to be accurately concave down. So this is the graph of the function f of x, capital f capital of x. The last example, I believe, would be this one. This is the cube root of x. So the domain is all real numbers, no problem with the cube root. Well, what happens if I take x to infinity? The highest power is c to the power x to the power 1 over 3 times x. So it's x to the power 4 over 3. It's raised to the power 4. So infinity to the power 4 is infinity. So when x approaches infinity or negative infinity, the graph goes to infinity. So it goes to infinity from here and from here. All right. What else? Is there horizontal asymptote? No, because of this infinity. Vertical asymptote, the domain or real numbers, so no vertical asymptote. No horizontal asymptote. What are the x-intercepts? The x-intercepts are 0 here. You put c equals to 0, y equals to 0. So cube root of x is 0, or x is 0, and x plus 4 is 0, or x is negative 4. So the graph passes by negative 4 and passes by 0. That's good. And the y-intercept is also 0, 0, 0. That's nice. Let us find the derivative. I use the product rule. Derivative of x to the power 1 over 3 is 1 over 3 times x to the power 1 over 3 minus 1 plus x to the power 1 over 3 times the derivative of x plus 4, which is 1. To simplify the first derivative, let us take x to the power negative 2 over 3 as a common factor. I can even take 1 over 3 to the common factor. Or let me not take it. So I'll have 1 over 3 times x plus 4 plus. Now x to the power 1 over 3 divided by x to the power negative 2 over 3. You subtract the powers 1 over 3 plus 2 over 3. It would be x to the power 1. So this would be c prime. I can take x to the power 2 over 3 down. And here I'll have 1 over 3x plus x. So 4 over 3x plus 4 over 3. To get rid of the 3, I can multiply by 3 over 3. So I'll have 4x plus 4 over 3x to the power 2 over 3. Now let us look carefully to c prime. C prime has a 0 when 4x plus 4 equals to 0. So when x is negative 1, c prime is 0. So this is a 0 of c prime. And c prime does not exist at x equals to 0. 0 belongs to the domain because the domain are real numbers. So we have something at 0. Either we have a vertical tangent line or a cusp, maybe, because the domain is all real numbers. And let me tell you here what is the difference between cusp and vertical tangent line. The derivative does not exist. Cusp, when you have something like this, okay? This is a cusp. This point here, this is a cusp. What happens, you have the limit at a, if this is a, if this is x equals a, then when x approaches, the derivative at a, what is the definition of the derivative at a? Limit when h approaches 0 of the function is c here. C a plus h minus c a over h. This is actually c prime at a. Okay. If c prime at a does not exist, then we will have a cusp at x equals to a. Vertical tangent line, the graph would go like this. At x equals to a, we have a vertical tangent line. Also here the derivative does not exist. But how to find out that we have a vertical tangent line? The limit here, when h approaches 0 of ca plus h minus ca over h, which is c prime at a, is infinity or negative infinity. Well, in both cases, it does not exist. But here, from both sides, when h approaches 0, from the right and from the left, it goes to infinity, both, or negative infinity, same direction. But here, 1 goes to infinity when h approaches 0 from the right, for example, and from the left, it goes to negative infinity. So it does not exist. We say it does not exist. So let us find out what happens at 0 actually. So let me find limit c0 plus h minus c0 over h when h approaches 0 from the right. What is c? It is this function. If I replace, what is c0? c0 is 0. Okay. So what is ch? 0 plus h is h. ch is h to the power 1 over 3. So I have the limit h to the power 1 over 3 times h plus 4. This is ch, isn't it? All right. Over h minus c0. c0 is 0. Well, this is the limit when h approaches 0 of h plus 4 over h to the power 1 minus 1 over 3. That's 2 over 3. And I can write this limit as h over h 2 over 3. That's h to the power 1 over 3. 1 minus 2 over 3 plus 4 over h to the power 2 over 3. And the limit of this is 0. Okay, cube root of 0 is 0. And now here, what is the limit? Well, 4 over 0 is infinity, but is it infinity or negative infinity? Because this is 2, so when I choose a small number to the right of 0.1, for example, this would be positive, so the limit is infinity. Also, limit h approaching 0 from the left of 4 over h to the power 2 over 3 would be infinity because I have 2 here. So even if I choose a negative number, negative 0.1, this would be positive. So the limit is infinity. So you can see that the limit when h approaches 0 is infinity of c0 plus h minus c0 over h. It's infinity. So I have a vertical tangent line at x equals to 0. So at x equals to 0, I have a vertical tangent line like this. Okay. And let me make the table of f prime, c prime, sorry. The domain or real numbers, we said c prime, where is c prime? This is c prime. 0, it does not exist as 0 and negative 1. So this is negative 1, this is 0, this is negative infinity to infinity, and this is c prime, and this is c. Well, this is x to the power 2 over 3, so it's always positive. So the sign of c prime depends on the numerator. If I choose a number greater than negative 1, 2 for example, it would be positive. So to the right of negative 1 it is positive, here it is negative, so it's decreasing, increasing, increasing. I have nothing at 0 because the first derivative is not defined. We know what we have at 0, vertical tangent line. So I can answer part A now. It is increasing on negative 1 to 0 union. Well, 0 is in the domain. So I can say from negative 1 to infinity, domain of f, I can say that from negative 1 to infinity, the function is increasing. And it is decreasing from negative infinity to negative 1. So up to negative 1, it is decreasing. It goes like this, decreasing. Is there a maximum or a minimum? Yeah, okay. There is a local minimum at negative 1. So the local minimum, in fact, is f of negative 1. And what is f of negative 1? Well, negative 1 to the power of 1 over 3 is negative. Negative 1 plus 4 is 3. So negative 3. Wow. So negative 1 and negative 3, that's excellent. 1, 2, 3, this is a local minimum. So I guess that the graph goes like this. And now it goes like this. Here I have a vertical tangent line. And it continues like this somewhere. It will continue to infinity. Okay, like this. what we can see later uh, when we find the second derivative. What are the concavity uh, regions? So let us find the second derivative, c double prime of x. Well, this is c prime. This is c prime. So c double prime would be 9x to the power. The denominator is 9x to the power 2 over 3 to the power 2, so that's 4 over 3. The derivative of the numerator is 4 times the denominator. So it's 12 times x to the power 2 over 3 minus the numerator, which is 4x plus 4 times the derivative of the denominator, which is 3 times 2 over 3, and that's 2, x to the power 2 over 3 minus 1, and that's negative 1 over 3. Let me take a common factor. I have 2x to the power negative 1 over 3 as a common factor. So I have 6. x2 to the power 2 over 3 divided by x to the power negative 1 over 3, subtract the powers, you get x minus 4x plus 4. Multiply the minus by the two terms. So I have minus 4x minus 4 over 9x to the power 4 over 3. Well, bring x to the power 1 over 3 down. 4 over 3 plus 1 over 3, it would be 5 over 3. And here I have 2x minus 4. So c double prime is 0 when x is 2. 2x minus 4 equals to 2x equals 4, x equals to 2. And at 0 also, c prime does not exist. So this is the 0, and this is 2, and c double prime. The signs of c double prime. All right. Choose a number greater than 2. 4, for example. It would be positive. 1. If I choose 1, the numerator would be negative. The denominator would be positive. If I choose negative 1, the denominator is negative. Negative 1 to the power 5 would be negative. The numerator is negative, so it would be positive here. So here it's concave up, concave down, concave up. So this is part C. I can say concave up from negative infinity to 0, union from 2 to infinity, and concave down from 0 to 2. And I have one inflection point, 2 and f of 2. At 0, we don't have an inflection point. We know at 0, it's a tangent line. So at 2, let me find f of 2 or c of 2. It is 2 to the power 1 over 3 times 6. So it's 6 times 2 to the power or cube root of 2. Actually, what about 0? Actually, 0, 0 is an inflection point. Why? Because it is in the domain of C. It is in the domain of the function. We have a tangent line at 0, but also it's an inflection point. So because up to here, the graph will be concave up, and starting from 0, the graph will be concave down. Up to where? Up to 2. So 1, 2, and from 2, so up to here it's concave down, and then from 2 it starts to be concave up. So this would be the graph, and it satisfies everything. So it's concave up from negative infinity to 0. Yeah, it's always here concave up to 0, and then it's concave down up to 2, and then concave up from 2 to infinity, and I have two inflection points. So this is the graph of the function, and I think this graph is okay, is accepted. Okay, this graph is accepted, and you can choose more points to check what happens at 3, at 4 exactly. Okay, that's the end. Thank you very much, and I hope you enjoyed curve sketching.